Today we are going to solve some problems from solid state physics or chemistry. Here is one problem. The problem says calculate the compressibility of NaCl assuming a repulsive potential of the form B by R to the power 9 to act between nearest neighbor, and the nearest neighbor distance R is equal to 0.281 nanometer. Madelung constant for the given system is 1.746. It means we have to calculate this compressibility of NaCl, and this compressibility of NaCl is also known as beta, and we know that here is the repulsive exponent from B by R to the power 9. That means value of n is given, it is equal to 9, and the Madelung constant value is given here 1.7476, and nearest distance is given here r equal 0.281 nanometer. Now we can rearrange these things in this way, that is value of n is equal to 9, so this is value of n, one exponent, and the value of r, this is equal to 0.281 to the power multiply 10 to the power minus 9 meter, and this is Madelung constant. For calculation of this one exponent, we have to know the value of E, that is charge of electron, it is given here, and the permittivity of the system, it is given here, and by substituting this value in the equation, this is the equation where this is one exponent and this is compressibility factor. On rearranging this equation, we obtain this. We rearrange this. On rearranging this, we can subtract this 1 from n, then this becomes n minus 1. Now we can substitute all values from here. This is value of n from here. Here is the value of n equals 9, and the value of r naught is given here. Similarly, value of A we can substitute, this is from here, and value of epsilon naught, this is here, permittivity, and value of E, this can also be substituted, and the value of pi is equal to 3.14, or we can substitute by pi by 22 by 7. So by substituting this value, we can obtain this relation, and its value become 9 minus 1, it means is equal to 1. On rearranging, this beta can be rearranged in this side, and it can be rearranged in this side, so that after calculation we obtain this relation from denominator and numerator. There are two values, and after calculation of this value, we obtain here value of beta, that is compressibility factor, and this is equal to 3.48 multiplied 10 to the power minus 11 meter square per n. This is the value of compressibility factor. And here is the next similar type of question, and the question asks that calculate the lattice energy of sodium iodide crystal in electron volt and joules per mole, having given equilibrium separation R naught, and its value is given here. R naught is equals 0.281 multiply 10 to the power minus 9, and also value of n is given here, n equals to 10, and Madelung constant is given here 1.75. So we have to calculate the lattice energy. Lattice energy means we have to calculate U naught or UR naught, that is at equilibrium distance, and its value can be calculated. To know this value, we also have to know value of compressibility factor, compressibility factor not permittivity of the system, and charge of the electron, that is, we know that this is given, and value of n is also given, value of A is also given, and we know this permittivity of the system, and we have to calculate this lattice energy. Now we can use this equation. Lattice energy of the system, U is equal to negative Avogadro's number, this is Avogadro's number, and A Madelung constant, Z1, Z2, this is are the charges of cation and anion, that is sodium and iodide, sodium ion and iodide ion. It means they are is equal to 1, and this one is equal to charge of electron, and this is one exponent is given equals to 10. Here we can see this is 10, we can substitute it here, and R naught is also given, this is R naught, and this R naught we can substitute here, and similarly E naught we can substitute here, and A is given, we can substitute it here, and value of Na we know, Avogadro's number. Similarly, this Z1 and Z2 are 1 because there are Na plus and I minus. This means Z plus is equal to 1 and Z minus is equal to 1. So by substituting these all things in this equation, we can obtain this type of equation. On solving this equation, we obtain this energy in the form of joule per mole, and to convert it into kilojoule per mole, we can convert it in this way, that is 77.359 kilojoule per mole. Then after we can convert it into electron volt per mole by just interconverting or by changing its unit conversion. So we can obtain both in electron volt and kilojoule. So this is the energy which our question asks here, electron volt and in joule per mole. Now here is the next sequence, and this sequence we have to rearrange it. This is not actually problem. This says that this is the lattice energy given UR equals A minus A R by A by R plus B by R to the power 9. The A and B are constants, and we have to show that the attractive energy here in this equation we can see this one is attractive energy and this one is repulsive energy, and the question asks to us that if this solid material is in equilibrium, then we have to show that this attractive energy is 8 times greater than that of repulsive energy. And to find this arrangement, we have to assume that attractive energy of the system, that is, let the stable configuration attraction energy A by R naught, this is attractive energy, and this is equal to phi A, this is attractive energy, and similarly the repulsive energy is equal to B by R to the power n phi R. This phi R and phi A, so these are from here, or we can just change these things. This is B by R to the power n, we can replace it by B by R to the power 9 because it is given here. So we can change. So and now we can take ratio of this phi A and phi R, that is attractive and repulsive. Then what can we obtain is equal to this one, and on solving we get A by B R to the power 8. This is equation 1. Now here is given UR is equal to negative A by R plus B by R to the power n. On differentiating this equation, that is, on differentiating this equation, we can get this result, that is, and this differentiating this equation at equilibrium distance is equal to lattice energy. On differentiating at equilibrium state means it is equal to 0. So we can assume that this all thing is 0, and only this part we can solve, this part. Now its differential form is A by R to the power 2, and its differential form is 9B by R to the power 10. So just sign a change there because we take differential form, and its negative 1 comes here, and negative becomes positive, and its negative part goes here and it becomes positive. Now this is positive part and this is negative part, and the product the sum of these two is equal to 0. It means we can arrange A by R to the power 2 is equal to B by 9B by R to the power 10. So on rearranging, it means if we place this R to the power n here and A here, then what we obtain is R to the power 8 is equal to 9B by A. So from equation first we can say that phi a by phi r is equal to a by b r to the power 8, and here r to the power 8 equals to 9b by a. So substituting this value in equation first, we get a by b multiply 9b by a, that is phi a by phi r is equal to 9 a by b 9b by a, and we can find lastly these are cancel to each other, and phi a is equal to phi r. This is attractive energy, we assumed it here. This is attractive energy at equilibrium state, and this is repulsive energy, we assumed it here at equilibrium state. Now we find the relation attractive energy is equal to repulsive energy, with this repulsive energy is just 9 times 9 times repulsive energy is equal to attractive energy for the system in a equilibrium state. And this is the arrangement what our question says, and our question this is the complete answer, and this shows that the energy of attraction is 9 times greater than energy of repulsion.